thank you very much for the very kind introduction. I would like to thank the organizers for organizing this great event and for their kind invitation for me to speak here today. So I hope everybody has drunk enough coffee, so they stay awake, right? So one can phrase this as a question: can we understand the spectrum of a linear operator if we understand the geometry of the underlying space? Now, just before the talk, Niels has already given the answer to me and said, no, we can't, right? But one might add, but we can sometimes. And let me start very smoothly and slowly with a finite dimensional result, which is more than 100 years old. So one way to understand the spectrum by geometric properties is the so-called Perron-Frobenius theory in finite dimensions. So this is part one. The Perron-Frobenius theorem. Now, that's a bit of a fake title for this chapter, because actually there is no single thing which is called Perron-Frobenius theorem, despite some people claiming this. So there are various versions of the Perron-Frobenius theorem, and I'm going to show you one Dutch result. And this is theorem 1 here. So let us consider a matrix T in R to the D times D. And assume that the matrix is positive. And now I write large or equal than 0. Some people would call this a non-negative matrix, especially in matrix theory. I'm going to call it a positive matrix in accordance with Banach lattice theory, because there are such operators that are called positive. And this inequality is meant entry-wise. So every entry is larger or equal than 0. Okay, now I'm interested in the eigenvalues, and I consider the so-called spectral radius. I denote this by R of t. So this is the spectral radius. It just means you take all the eigenvalues, you take their modulus, and then you take the largest of those numbers. That's the spectral radius. And I assume that the spectral radius is 1. One doesn't really need this assumption. It's just to facilitate the statement of the result. Yeah? You write it down in an easier way. Okay. Do we need something else? No, we don't. And the result is then you can consider what is called a peripheral spectrum of the matrix, and it's when you take the spectrum. So there's a sigma of t, but it doesn't mean just a set of eigenvalues, yeah, spectrum, and you intersect it with the so-called spectral circle, which is the unit circle here noted by t. So this is the set of all complex numbers of modulus 1, which is the maximum modulus of all eigenvalues. So this is the circle where you have some eigenvalues of maximum modulus, right? And the result is that this peripheral spectrum is the union of subgroups of the unit circle. So by subgroup, I mean subgroup of the multiplicative operation on the unit circle. This is a union of subgroups. So now, instead of first asking why is this true, one should first try to even understand what the result actually says, right? So let me make an example. Examples. So the first example is a 2 times 2 permutation matrix. This here. This is the eigenvalue is 1 and minus 1. Namely, the eigenvector is 1, 1, and 1 minus 1. So here the spectrum is indeed a subgroup of the unit circle. Minus 1. Okay. Now let's go slightly further, take 3 dimensions. What's a nice 3-dimensional example? Part B. Let's call this matrix maybe S. Let's take another permutation matrix of a cyclic permutation. For instance, this here. That's a permutation matrix belonging to a 3 cycle on 3 dimensions. Now the spectrum has 3 numbers, namely all 3 roots of unity, right? So the spectrum here is, if I call the first root of unity psi 3, then it's psi 3 to the power 0, which is 1, and then it's psi 3 itself, and then it's psi 3 square. And this is indeed a subgroup of the unit circle with 3 elements. Okay. Now I said it can be a union of subgroups. How can I achieve an example where I have a union of subgroups of the unit circle? Well, let's see. So I want to take a 5-dimensional example. I can take, let's call it R, just the direct sum, right, of S and T. So 5 times 5 matrices, and then I have to unify those spectrum. So the spectrum R is the spectrum of T unified with a spectrum of S. And then we need to have a union of subgroups, which is itself not a subgroup. Okay. So this is somehow how we should think about this result. And well, actually, here the spectrum is only a subset of the unit circle, and the result is, well, it can happen that there are other spectral values which are smaller than 1 modulus. Okay. But if you consider those which have modulus 1, it looks like this here essentially. Okay, now why is this true? And what does it have to do with geometry? But first of all, the geometric part here is this inequality, because a matrix having all entries non-negative means that at least the standard cone in Rn invariant. Yeah? The standard cone is a geometric object. And one can, for instance, ask, okay, is this still true if I replace the standard cone with another cone which is invariant? And the answer is no. Can consider in 3 dimensions the so-called ice cream cone, which looks, well, like an ice cream cone, right? And then you can consider a rotation matrix, which leaves the ice cream cone invariant. And then you can produce a lot of examples with eigenvalues somewhere on the unit circle, which are not do not form a subgroup. Okay, so it has to do with the geometry of the cone. That's where in this theorem geometry plays a role. Now, why is this true? I don't want to show you the general proof, but I want to show you a proof in a special case, because it's, well, we're going to need it afterwards, the argument. So, proof of theorem 1. And in case that, so the special case I want to consider is power-bounded matrices. So I consider the powers of the matrix, G to the n. I consider the norm, just take your favorite norm on the matrix space. They're all equivalent in finite dimensions. And this should be bounded. This power boundedness. Okay. In this case, I'm going to show you the proof now. And in the general case, one can somehow reduce to this case. How do we do this? Well, I consider this peripheral spectrum here, okay? Sigma T, sigma of T, intersected with the unit circle. So those has finitely many elements, because we're in finite dimensions. So I call them, let's say, lambda 1, maybe lambda m. Now, those are eigenvalues. I claim those eigenvalues are semi-simple. What do you mean by semi-simple? This means the geometric multiplicity coincides with the algebraic multiplicity. Or in other words, if I consider the Jordan normal form of this matrix, then the Jordan blocks that belong to those eigenvalues, they're all trivial. Yeah? They might have geometric multiplicity, strictly larger than 1, but the Jordan blocks are trivial. They do not contain non-trivial parts. Why is this true? Well, if you write down the Jordan normal form and you take those powers here, and there were a non-trivial Jordan block, and you can compute the power of Jordan blocks, and then you can see that this power boundedness condition is not satisfied. So the power boundedness condition implies semi-simplicity of those eigenvalues. Semi-simple. Okay, now I can do a bit of complex analysis, vector valued or matrix valued. I consider the so-called spectra projection, which is associated to this part of the spectrum. So if you know a bit of operator theory and what a spectral projection is, that's good. If you don't know what a spectral projection is, you can think of it in the finite dimensional case as follows. You can say, okay, well, I have again the Jordan normal form, and this splits my space into 2 subspaces. One subspace which belongs to those Jordan blocks with those eigenvalues, and one subspace which belongs to all the other Jordan blocks. Okay. And now the projection onto the space that belongs to those eigenvalues along the other space, that is called spectral projection. Okay, so I call it P like projection. Let P denote be associative spectral projection. Now the interesting thing is to consider just the spectral space that belongs to P, so the range of P. So the range of P, plug in our D into P. I say, well, the same simplicity of those eigenvalues, so that the Jordan blocks are trivial. This means precisely that this is the direct sum, the associated eigenspaces, right? It's precisely what happens if you look at the Jordan normal form. So this is kernel lambda 1 minus T plus and so on plus kernel lambda n minus T. Okay, in other words, T operates on this space as multiplication with lambda 1, as multiplication with lambda 2, and so on, and as multiplication with lambda n. Okay, now this is useful because I'm claiming that the spectral projection P is also positive. And we can see this by using this here. How can we do that? Well, take your favorite number on the unit circle. I claim I can find a subsequence of the natural numbers, nk, such that your number, let's call it lambda, your complex number lambda 2 nk converges to 1. This is clear if lambda is a unit circle. If lambda is a root of unity, because then you can take a periodic sequence. And if it's not a root of unity, then the powers of lambda are dense in the unit circle, and then you can again subtract the subsequence. That is true for 1 lambda. Now you can, I'm not going to show this, you can also do this for several numbers. You can in fact find a subsequence nk of the integers such that lambda j to nk converges to 1 as k to infinity for all j from 1 to n. This goes simultaneously for finitely many of them. By the way, you could even do it simultaneously for all numbers on the unit circle, but then you would need a net instead of a sequence. But anyway, this suffices here. Okay, now what does this mean? This means, look at this sequence here. So on the range of P, it acts as multiplication with those numbers to the power nk, but it converges to 1. So this means it converges to the identity if I only consider the action on the range of P. But if I consider the action on the kernel of P, well, on the kernel of P, that's the rest of the space which does not belong to those eigenvalues. So on the kernel of P, the eigenvalues of the remaining operators are strictly less than 1 in modulus. So this means the powers of P converge to 0 on the kernel of P. So this converges to 0 on the kernel of P. But this means on the entire space it converges to P. So P is the limit to the nk. And T was positive, so P. Okay. So the spectral projection is positive. And here you really need power bounding. This is not true if you don't have power boundings. Okay, now why is this useful? Well, if you know a bit about vector lattices, you can show that if you have a positive projection of vector lattice, then the range is again a vector lattice. Open parenthesis, small subtlety, it might not be a sublattice. Just another vector lattice with different lattice operations. Close parenthesis, right? Okay, so P to the RD is a vector lattice. Okay. Finite dimensional vector lattice. So it's isomorphic. Every finite dimensional vector lattice is isomorphic to R to the another dimension. So it's isomorphic as a vector lattice to R to the D tilde. Okay. Okay, and I claim that T acts positively on this restriction. Okay, that's clear because T acts positively on the entire space, so it acts positively on this restriction. But now the next point is even the inverse of T. So T is invertible. T is invertible on this space because you split off all the spectrum, which is not on the unit circle. So T restricted to the space does not have 0 in the spectrum, so it's invertible. And it's even power bounded in both directions. So if you take T restricted to the range of P, to the power n, and let n run through the integers, positive and negative, stays bounded. Again, because I split off the rest of the spectrum. Okay. Now I say the inverse of T is also positive on the space. Why? Well, T restricted to P inverse is just, you see, the identity on the range of P. The identity can be written as this limit here on the range of P, or see it here. But this means if I subtract 1 here in the exponent, then I get the inverse of T, right? So that's positive because I can write it as also as a limit of T to the nk minus 1. That's also positive. So this means T is positive, inverse is positive. It's a lattice isomorphism on R to the d tilde. Now lattice isomorphisms on R to the d tilde are very, very easy to describe. They're essentially permutation matrices where the ones are replaced by different positive numbers. Those are the lattice isomorphisms on R to the d tilde. Okay, and we also know, I just mentioned this, double power boundedness of this operator. So supremum n runs through set. Finite. Now I'm not going to show this detail now, but using this you can show that your weighted permutation matrix is similar just to a permutation matrix. So this implies that T restricted to the space similar to a permutation matrix. Okay. But permutation matrices, there we know the spectrum. They are just some permutations can be written as disjoint compositions of cycles. So it looks precisely like this here. So that's the proof because the spectrum of this here is a union of subgroups of the unit circle, but the spectrum of this is precisely the set with which we start. So we have it. Okay. So this was first part of the talk. Old stuff. Caron and Rovinus didn't show by this proof, but anyway, it's a nice proof. Okay. Now, did we really use finite dimensionality? Well, let's see. Part 2, the Banach lattice case. So this is a conference on Banach spaces and Banach lattices. I need to mention Banach lattices. Banach lattice case. So here's theorem 3. So let E be Banach lattice. Sorry, it's German, less English. Be a Banach lattice. And T a positive operator from E to E. Now we talk not only about eigenvalues, we're talking about spectral values. Yeah. And I again assume that the spectral radius is 1. Okay, and now I make 2 further assumptions. The first one is this here, power boundedness. Power boundedness. And the second one is, so for the talk now I'm only going to consider compact operators. This is strictly speaking not really necessary. One can weaken this assumption, but I do not want to get involved with too much technicalities about spectral theory of quasi-compact operators or whatnot. Let us just for the simplicity consider positive operators. So compact operators, sorry, T compact. T compact. Okay, so it makes a unit ball into relatively compact set. Then the same thing is true over there, Banach lattices. Then I intersect the spectrum with the unit circle. This is a union of subgroups. By the way, it's also finite by the compactness, but that's not so important now. Subgroups of the unit circle. Okay. Now, why is this true? For precisely the same proof. You can just copy the proof. It's exactly the same, because we never used here that R to the D is finite dimensional. We just used that the spectrum here is finite, and this is true due to the compactness. And the spectral space, so the range of the spectral projection P, is then also finite due to the compactness, and they can do precisely the same proof. So, same proof. Yes.
So what about the convergence of the powers? Is this pointwise now, or you just have it in
operational? Okay. Yes, so in operational. Please.
So when you talk about the spectrum, usually that to me is a complex notion, right? So how do you, what does the spectrum and spectral radius exactly mean here?
Yes. So it's a complex notion what works on the complexification of the Banach lattice. Right. Good point, I should have mentioned this. So every Banach lattice has a complexification, and in general, every Banach space has a complexification, which I'll use at the end of the talk. And one tries, so E is a real Banach lattice, but the spectrum here denotes the spectrum of the extension of T to the complexification of E. Like here. Yes, okay. So the same proof. Now, I mentioned in passing, you can dispose with one of those two assumptions, the one which you like. You can get rid of this or of this, and it's still true, but this is more difficult to show, especially if you dispose with the compactness. That's a much younger, well, not so young, but it's from much younger than this year. So this is more than 100 years old, and this is 50 years old without the compactness due to lots from 1968. But this uses ultra power arguments without compactness. That's a bit more involved. So probably interesting for some people here who like ultra powers, but not what I'm going to talk about today. Okay. So we are closing in on the present, right? So 100 years, 50 years, okay. So why do we even need that Banach lattice? Well, strictly speaking, we don't. Okay, we need a Banach space and its complexification, right? But, well, we need that E is lattice ordered because, see, where did we use the lattice order? We needed that this here is a vector lattice. And this was true because P was positive, okay? And because R to the D was a vector lattice. So strictly speaking, we do not need that E is a Banach lattice. We need that E is a vector lattice in the Banach space. This is weaker. Okay, so here's an example. Example 4, actually. So your the favorite space of many people here maybe the Lipschitz functions. I'm not sure if the favorite space, but many people mention it. So M is a metric space. You consider the Lipschitz function which is 0 at a base point. This is the vector lattice. Okay, just take the pointwise supremum of two functions, and you know the Lipschitz norm. Then this is a Banach space, and the cone of positive functions in the vector lattice is closed. Yeah. But it is not a Banach lattice because, well, it can happen that you have a function, for instance, on the unit interval, the identity function, and then you have a smaller function which oscillates very, very quickly, and then the smaller function is going to have a larger norm, right? And this is incompatible with the typical requirement for Banach lattice norms. So it's a Banach space, it's lattice ordered, but it's not a Banach lattice. But still, this theorem applies here because we just don't need the property of the Banach lattice norm. Okay. Another example is similar spaces of first differentiability order. So P is between 1 and infinity. 1 is the differentiability order of a set omega in RD. This is also vector lattice. And if you're interested in fractional Sobolev spaces, now where's Mitchell? Yes. So Mitchell yesterday told me that for fractional Sobolev spaces, it even works for slightly higher differentiability order, which surprised me very much. Still remains a vector lattice. But it is not a vector lattice if you, for instance, write W2 here, because then the modulus of a twice weakly differentiable function might no longer be weakly differentiable. Okay, so we can get rid of Banach lattice. We need a vector lattice, which is also Banach lattice in the north. Vector lattice, which is also Banach space, and the cone should be closed. Okay. Problem. What about the following spaces? Ck omega bar if k is larger than 1. We're about missing. So omega d with nice boundary maybe. Take the k times continuously differentiable functions whose derivative all extend to the closure of omega with the usual norm. So you take the supremum of the infinity norms of all those derivatives, right? There's a nice Banach space. It's also ordered, so it has a cone, the order with respect to the usual pointwise order, but this is not a Banach lattice. Yeah. This is not a Banach lattice, because differentiable function modulus might not be differentiable, right? Because you get a corner then. So is this theorem true on the space? Good question. Now I claim, while this space is not a lattice, it still behaves somehow lattice-like. And that's a nice insight I want to convey today. So this is part 3. Lattice-like ordered spaces. Okay, so let me phrase this. Maybe I should first introduce the following notion. So to make sure we all understand what we're talking about, I need to define now what I mean by an ordered Banach space. Okay, so an ordered Banach space. And again, I talk about the real spaces, and whenever I talk about the spectrum, I mean the canonical extension of an operator to complexification of the real space. So an ordered Banach space was told yesterday not to abbreviate it by BS. I'm going to abbreviate it by BSP. Ordered Banach space. That's a pair. E is the Banach space, a real Banach space, and E plus. That's called the positive cone, just as in a Banach lattice. And you say, okay, E plus is closed. And what do you mean by cone? I mean, if I take two positive or two non-negative numbers alpha, then alpha times the cone plus beta times the cone is again in the cone. This in particular implies that the cone is convex. And I assume that is not too large. For instance, the entire space would satisfy this, but I do not want the entire space. I want that E plus does not contain any infinite lines in both directions. What I have to do to ensure that this does not happen is I have to require that the cone intersects minus the cone only in 0. Okay. No, this is our Banach space. Banach lattices are examples. Those are examples. There are a lot more examples. If you take the Z-star algebra and consider the self-adjoint part with a spectral order, this is an ordered Banach space. Okay, but it's not a lattice unless the Z-star algebra is commutative. And for non-commutative Z-star algebras, the self-adjoint part is never a lattice. This is a result by Sherman from the 50s. Okay. Now, I call, and that's the next definition, I call such a space, and the number is 5. An ordered Banach space E plus is called projectively lattice ordered. If now, well, projectively, I want to talk about projections. If P is lattice ordered with the induced order, so the restricted order, is lattice ordered for each positive finite rank projection P. Finite rank projection okay. Now, how is this definition motivated? Well, by the proof of the theorem, right? Because what did we need? We did not even need that the entire space where we started, RD, as a lattice. We only needed, so the only part where we needed a lattice is this line here in the proof. That the range of P is a lattice. So this means, and that is precisely what I assume, because P is always a finite range projection, finite rank projection, since they start with a compact operator. Yeah. So this means if I require this definition, the theorem remains true. So that's the point of the definition, okay? So theorem, the infinite dimensional case was theorem 3, this remains true. Or those spaces. Let's read it. And essentially this here is a geometric condition because it tells us something about the cone. If you take a Hilbert space and you take the bounded linear operator in the Hilbert space, that's the star algebra, you take the self-adjoint part with the usual cone, so the self-adjoint operator is positive if and only if its numerical range is contained in the positive real line, yeah? The not negative real line. This is not only not a lattice, but this is the complete opposite of a lattice. It's even a so-called anti-lattice, whatever this means. This does not have this property. So there are ordered Banach spaces which are very far from this property. But if you have the property, it's something geometric, and that has a consequence, this theorem for the spectrum. Okay. Now, analyzing proofs and writing down nice definitions is easy, right? Yeah, but it's also pointless if you don't have examples of those spaces. Okay, so what are examples of those spaces? First of all, every Banach lattice is an example of such a space. We use this in the proof of theorem 3. Every lattice ordered Banach space, so every, for instance, those spaces, also is an example of such a space. Okay. But we need more, of course. We want more examples. What about those spaces? What about C of K spaces, which are not lattices? Well, okay, first remark. If omega is one-dimensional and k is 1, this is a property which some of you might know. It has the so-called Riesz decomposition property. The Riesz decomposition property means if you have two positive vectors, f and g, and you take the order interval from 0 to f plus g, it's the same as the order interval from 0 to f plus the order interval from 0 to g. This is the Riesz decomposition property. This is weaker than being a lattice. Every lattice has this property, but C1 of the unit interval also has this property. Now, I won't write it down, but one can show that spaces with the Riesz decomposition property have this property always. This is true. But for large K, this does not have the Riesz decomposition property, so this doesn't solve our question. Okay, so now I'm going to write down a theorem which somehow solves this question. And this is theorem 6, actually. Yes. So let E be an ordered Banach space, F a Banach lattice, and I'm doing like this here, and A from E to F. Injective, let's see whether the camera can handle this. Injective map, a bipositive map, okay? What means bipositive? Well, it means J of F is positive if and only if F is positive. This means bipositive, right? Injective bipositive with dense range. And I want this map to be majorizing. Majorizing means and for each vector in the codomain, let's say in the let's say that way, there exists a vector in the domain such that the mapping of E dominates. This is majorizing. Those are the assumptions of the theorem. So we can somehow embed E into a Banach lattice. Yeah? And under these conditions, E is indeed projectively lattice ordered. Then E is projectively lattice ordered. Sorry, but also difficult to write over there. Okay. So under this condition, we have projectively lattice ordered spaces, and then the theorem here holds, and we have this nice, beautiful symmetry result about the spectrum. All right, you erase this part here. Make up questions if you like.
Can you repeat the definition of bipositive? Sorry.
Yes, bipositive means, so positive means if small e is positive, then J of small e is positive. And bipositive means that J of small e is positive if and only if small e is positive. And so I cannot talk about the inverse function because it's not onto, but it just means the image of a vector is positive if and only if the vector is positive. Okay, please.
Yeah. When you define your definition 5 of the projectively lattice order, right? You want P of E not just to be a lattice, right? But you need it to be compatible with the structure from E plus, right?
Right. So by being a lattice, I mean a lattice with respect to the order inherited from E. So you intersect the cone of E with PE, and it's new cone of PE, and you can show that this is the same as P applied to the cone because P is a projection, and this is the order, and you want it to be a lattice with respect to this order, right? Sure. Good point. Yes. Thank you. Please.
Sorry, for the complexification, you don't need something for the existence of the modulus.
No, because for the complexification, I don't need to complexify the modulus. So in Banach lattices, I can do it, but to define the spectrum of the operator, I do not need to complexify the modulus. So you can do this on every real Banach space without order structure. A real Banach space and an operator on it, and you complexify the Banach space. Then you extend the operator to the complexification in a unique way, and then you define the spectrum of this operator to be the spectrum of the original real operator. And this does not depend on the choice of the complexification. So it's not, you don't need a complex modulus to exist. Thank you. Please.
So going back to the Perron-Frobenius theorem, so you not only proved what you claim you proved, but you proved something more, right? That you decompose your space into part with the small spectrum and then into a bunch of just permutations.
Right.
So exactly. Does it still hold for the?
Yeah, that's true. Yes.
Okay. So the similarity between the permutations and the pieces of your operator, are they somehow order preserving, or they just lose this structure?
So you get which similarities? I mean,
so you say that in the proof of the Frobenius theorem, you get a bunch of pieces of operator which are similar to the permutations, right? But the similarity, the matrix that
this one, yes, this is positive preserving, yes.
Okay.
Similarity is positive, is bipositive, yes. Exactly. So it's a positive isomorphism in the category of positive Banach spaces, of order Banach spaces. Right. Thank you. Okay, great. Let's go ahead. Okay, so erase this here. That's it. Okay, then let's go on. So what are examples by theorem 6? Well, for instance, so example 7. C of K spaces. Because they embed into C of omega bar, the continuous function is the Banach lattice. The embedding is dense, the embedding is bipositive. The embedding is just the canonical inclusion of that, right? It's bipositive, obviously. And it also has this domination property, which follows immediately from the fact that the constant one function is in the space. Yeah. So the constant one function times the number dominates everything in Z of omega bar. So it satisfies all the assumptions of theorem 6. So those are indeed projectively lattice ordered spaces. Another example is circular spaces of higher order differentiability, WKP. If, let's say, omega is bounded, maybe with nice boundary, I don't write this down, and the dimension D of the space times K times the integrability index, the dimension is smaller than the differentiability index times the integrability index, because this implies for nice boundary that this here embeds into the continuous functions again, and then you can use the same argument. So this is also projectively lattice ordered, although it's not a lattice for large K. I don't know what happens for K between 2 and this number here. Don't know. Nice question. If you would like to answer it, great. You can also, maybe your team is interested in this, you can also have certain spaces of holomorphic functions which have this property. But I don't want to write, I want to write down the details because that's a bit more, takes a bit too much time. Okay, now I said we were closing in time. We started 1910. Then we had a result from Flotz from 1968. Now we have this notion here, which is from my PhD thesis, 2016. We're closing in. Next example is the result from yesterday. So together with Vladimir, we found out something which I've been wondering about for several years. Now let E be an ordered Banach space. Banach space, which is also lattice at the same time. It's a lattice. Now, what we could show yesterday is that actually this implies, so it's a lattice with respect to the order induced by E plus. What we could show yesterday that this implies automatically that the lattice operations are continuous at the point 0. So the mapping which maps F, modulus of F, is continuous at 0. Okay, so that's application of the open mapping theorem applied to the appropriate choice of norms, which found out. But, okay, so this was the result from yesterday. Now here's the but, which is of course known. But in general, this is not continuous at other points than 0. In general, not continuous at other points. And I show you an easy counter example, and after this counter example, I show you why I show you the example. Okay, so counter example. We take the Lipschitz functions. On the unit interval without base point, and as the norm of F, you take the Lipschitz, the optimal Lipschitz constant of F, well, maximum with the supremum norm, and so this is the maximum here. And I need the maximum because I'm not sure it's a base point, so I need something to ensure that the constant one function does not have norm 0, right? Okay, this is such an ordered Banach space, which is a lattice, but not a Banach lattice. Now I claim the lattice operation, the modulus, is not continuous in general. And I show you this by a picture. So here's the point 1. Take the following function. So this is approximately the identity function. I've pulled it down a bit by the distance 1 over n. This is 1 over n. Drag it down by 1 over n. Okay. Now, if n tends to 0, this clearly converges in the lattice norm to the identity function. Now consider the modulus. So this is Fn. So the modulus is looks then like this, right? This is the modulus of Fn. Okay. Now I take the identity minus Fn, okay? So this then looks like so this is 1 over n minus 1 over n, that's the identity. Yeah. And this here has slope 2 for every n. So this does not converge to 0 in the Lipschitz norm because it was a slope 2 at this point, at this position. Okay, so I've shown that modulus Fn does not converge. So I've got the modulus, sorry. That modulus Fn does not converge to modulus identity, although Fn converges to the identity. So this means the modulus function is not continuous at the identity function. Okay. Why is this nice? Okay, great. Why is this nice? Well, it's nice because if you consider the following space, the vector valued continuous functions from the unit interval into the Lipschitz functions. So those are continuous functions from nice space into a vector lattice. This is not a vector lattice. Why? Well, if I take a function which is continuous and then I take the modulus, then it might no longer be continuous into the space because I've shown that the modulus is not continuous, right? So that's not strictly a proof. You can also prove it, but that's essentially the argument why this here is not a vector lattice. But still, it is projectively lattice ordered. Why is this? Because I can apply my theorem 6 over here. It embeds into the continuous functions with values of the continuous functions. And the embedding has all those properties which can be easily checked. And then I see, okay, it's projectively lattice ordered. So the theorem remains true, although this is not a vector lattice. Okay, so this was a nice example which I decided to show here. I decided yesterday because I wanted to advertise this the result that Vladimir and I improved yesterday. Okay, great. Last part of the talk. So this is then section 4. Non-order spaces. Let's forget about positivity. Non-order spaces. So, okay, without positivity, you can't prove anything, right? But, well, why did all this work in vector lattices? The reason is essentially, if you analyze the proof, which I have now erased, it was that we got a lattice isomorphism on the range of the spectral projection P. This was a finite dimensional vector lattice, so R D tilde. And the lattice isomorphisms there are essentially permutation matrices up to, let's say, multiplication with non-zero numbers. And those have a very easy structure. So there are not many lattice isomorphisms on finite dimensional vector lattices. This was the reason why all this worked. Now, okay, if you forget about positivity, lattices and all that, I need another geometric condition because I'm still giving a talk about geometry of Banach spaces, right? Or geometric properties. Let's assume we don't have positivity. Let's assume we have contractivity of a map. And for instance, in LP. So, theorem. And this is then 9. Theorem 9 is. And let's work on LP. Now here I mean a real valued LP space, that's important. I work on a real valued LP space. It doesn't work on complex spaces. And by the spectrum, I again mean the spectrum of the extension of the operator to the complex valued LP space. Okay, but this is real valued. Okay. Take an operator which is contractive. Instead of positive, I now assume contractive. Norm at most one. Okay, empty compact. Now I will write, okay, then consider the spectrum of T intersected with the complex unit circle. Now this is not going to be a union of subgroups or something, because on a finite dimensional space, take minus the identity. It's only spectrums minus one. But I want to claim, though maybe it's not true, but I would like to claim, then this consists of roots of unity only. That's what I would like to claim. Now, if I were you, I would say nonsense. It's telling us bullshit, right? But that's not true. Because you see, take P is equal to 2 in R2, so the two-dimensional Euclidean space, take a rotation matrix. All the properties, but you can choose every angle you would like to the rotation. And then the spectrum does not consist of roots of unity. You can produce every eigenvalue of the unit circle you'd like to. Hey, you caught me? Not true? Well, if P is not 2. So I have a counterexample. I always accept for your counterexample, right? But it's indeed true. And the reason is precisely that you can't do this example. You can't do rotations because rotations don't leave the LP unit ball in R2 in very end if P is not 2. And that's the proof reduces to the two-dimensional case. It uses a clever argument of Lewis from the 70s. He did essentially this in the finite dimensional case. In the finite dimensional case, but you can extend it to the infinite dimensional case because due to the compactness, it's essentially a finite dimensional result. You can also extend it in various different directions. You can try to get rid of the compactness by using ultra powers and using some different assumptions. But let's keep it with a simple thing here. And why I wanted to use this here, well, I want to make one more reference to talk from yesterday, namely to Mary Angelica's talk. We were talking about spaces where there are not many isometries, right? And this here can be generalized. So generalization. LP can be replaced by a space. So a real Banach space, E, reals again, such that if I consider the two-dimensional subspaces which are one complemented, they should not be isometrically a Hilbert space, such that no one complemented two-dimensional subspace is isometrically a Hilbert space. Hilbert space. Then it's still true because it's precisely this two-dimensional thing which I told you. With the counterexample you would like to build with the rotation, you can only build those rotations if you have a two-dimensional space which is a Hilbert space. And the general case can be reduced to this here. So it's still true. And now the question is, which spaces have this property? Right? Which spaces have this property? And in infinite dimensions, so for instance, LP has those properties, P is not 2. This follows from a result of Ando, which essentially says if you have a contractive projection, or let me put it differently, if in an LP space you have a one complemented subspace, then it's again an LP space. With respect to different orders, so this is not about order, but you get an LP space isometrically. This is at least for finite measure spaces due to Ando and was later generalized. Okay, and then you can ask, okay, just for fun, let us ask what happens in finite dimensions. Let's see. So if dim E is infinite and is finite, then this is equivalent to a property which relates to isometries and the existence of very few isometries, namely, this is equivalent to the isometry group of every one complemented subspace of E is finite. That's the same result. Okay, and this equivalent is also proved by Lubitsch, the 70s. 27. So this is the last result. So this very last result has nothing to do with my work, but I wanted to mention it because it's related to this result, which is related to the spectrum, understanding the spectrum by geometric properties, and it's related to the talk yesterday for Mary Angelica. So I think that's a very nice conclusion for the talk. Thanks a lot.